Welcome back, Math 9. Today we are continuing our lesson number 1, or chapter 1 if you will, probability in society, except today's part 2. Last time I asked you guys to do 4 questions that I posted on this previous lesson video. Today I'm going to go through several. Some of the questions I ask you just as an assumption, or identify, explain type of questions. I'm elaborating a little bit more, so it's more than a simply going over your homework question. And by the way, this first half of the unit, statistic unit, we're talking about most of a scientific approach of how to evaluate the statistic data, so you don't have a lot of calculation, just for the heads up. So the first question, part 1. There's a guy, John Guy, noticed that in the last month, 70% of the time, and if you haven't highlighted or anything, please do so. 70% of the time bus was 3 minutes late. So he takes his time with breakfast only. So the assumption that this person made, first of all, is this 70% of the time is in fact experimental probability. However, this person 100% considered that as theoretical probability, which is technically a problem that can come out, because just because it's 70% of the time, I know it's more than half, but how can you bet the fact that the next one will be 3 minutes late? So how would this probability would change? There are several factors. So today we're going to focus on some factors that actually can change the probability. One of them in this case can be a weather. This portion was not on the homework, so please write it down. Number 2, situation, traffic perhaps. And number 3, any type of accidents, right? This is one of the reasons why when you guys use any of before COVID time, if you go from any places for field trip and so on, and the fact that you need to write down several agreement form, one of them is possible injury form, and when it comes to that, traffic accident is possible, even though theoretically it doesn't work when it comes to that, assuming that the driver is perfect and those kind of things. But experimental probability, it may happen. Question number 2, I'm going to highlight several parts first. Lately, John Guy's math teacher checks homework 4 days a week. So John Guy makes sure he has time to complete his homework today. So assumption that he made is technically the number of events. Of interest. First thing first, maybe the previous week was let's say full week. So 4 days a week, that means 4 over 5 when it comes to school day. So that means 8 over 10, so 0.80, or you can say it's 80% probability. Like I said, this is an experimental data. It's not theoretical data. Maybe he does all the time. But how would have the probability change in this case? Well, what if it's a short week? This is one thing that I can think of. So what I mean by that is we have Monday, Tuesday, Wednesday, and Thursday. Imagine that's the only case. Then, based on this 4 days a week, that means, does that person check 100% possibility? Do you get the idea in here? Because according to the sample size of that short week, Monday, Tuesday, Wednesday, Thursday, 4 out of 4 event is 100. Or if you kind of forcibly put this possibility 80% into the short week, then in that case, the maximum that is closest that you can get is 3 over 4, which is actually 75%. So there is an absolute change between the probability data. The third part, the question says, at school, John Guy and his friends agree that their lacrosse team has a 95% chance of making the final. So when it comes to this probability situation, one assumption that I can say is prediction based on previous data. So that means if I use the term that we learned before, it's kind of similar as extrapolation. Even though it's not a linear data that we're talking about, extrapolation was a one where, for instance, we have random data like that. We're trying to predict what's happening in future. Will it happen like that? Hard to say. In the sports event, what would the probability would change? Well, there are several cases. Since this is a sports, weather can play a huge role if it's outside. What about injuries of the players or any type of absent? You got the idea. Or it can be a little bit number of foul, condition of the player, you name it. One of the last question of the first question was, in health class, John Guy's teacher reads a magazine that claims 172 out of 1,000 male smokers develop lung cancer, but only 13 out of 1,000 male who do not smoke develop lung cancer. So in this case, I'm going to highlight things a little differently in here. One of the statistic talk about 172 out of 1,000. Another statistic talking about 13 out of 1,000 who's talking about non-smoker, and this was a smoker situation. So if you think about the statistic perspective, we're actually talking about statistic number one, statistic number two. We're talking about two different independent studies. So these two data shouldn't be overlapped because it's independent study. If I look at the statistic value in here, the first one, which is a smoker, according to this study, it is 172 over 1,000, so 0.172. Fancy way of saying this is 17.2% possibility of having a lung cancer patient because of the smoking. On the other hand, when it comes to a different statistic, 13 out of 1,000 develop. So in this case, 0.013, so 1.3% is a one that will develop the lung cancer. If you just look at mathematically, and if you separate those statistics, it does make sense because one part talks solely about smokers in 1,000. The other one talk about non-smokers of 1,000. I have the feeling that these two studies doesn't overlap because I know the denominator is basically 1,000 and 1,000, but it must be two different sample group. The reason being is, if you think about the other side of the coin, then 100 minus 17.2 is, well, what is that? Is that 82.8%? 82.8% should be the non-lung cancer patient. But if you look at the other one, this is 98.7% of population that doesn't develop any cancer. So 82.8 versus 98.7, those two do not overlap. So that's one of the reasons why I mentioned that these two studies are independent study that probably did 1,000 for one of those random sample and 1,000 for another. How would this probability would change? Well, again, when it comes to this, it's 100% experimental probability. So that means if the group happen in a different group in different location, then things can be completely different. For example, there are some study that says lung cancer can develop more if you have whatever gene code and then it's inherited from either mom or dad, something like that. Genetic can also play a huge role. Then we're gonna have to think about that factor because that can change the probability. So my question is, can we completely move away from assumption? Is there anything that we can identify, any reliable factor that influence probability? And yes, there are. Those are the ones that we actually look at previous questions answer. So I want you to look back in there. And like I said, if I put some reliable factor that influence probability, I guess one of them can be a sample size. Second one, probably, this is the trickiest one, experimental versus theoretical. And most of the time, experimental probability give you, how can I say, a lot of assumption in there. Our goal is try to go from experimental to theoretical, but going there is quite tricky. What other reliable factors that influence? Well, independent statistic. What I mean by that is if one statistic data is dependent on others, then both of them, because of one of the simple change, can affect the whole thing. So independent statistics is something that I can think of. Number 2, question was explain how some of the decision is based on theoretical probability, experimental, subjective judgment, or any combination of those. So let's go through that. It is Ozma's experience that 4 out of 5 times the prize in the cereal box is found at the bottom of the box. So Ozma opens the bottom of the cereal box to find her prize. So first thing first, there's a keyword, experienced 4 out of 5. That already give you the idea that this entire statement is concluded based on the experimental probability. That's one thing that I can notice. The second one, obviously we have a subjective judgment in here. The reason being, because of the experiment, which give you about 80% possibility, this person was relying on that 80% possibility for the next event too. So that's why. The next event talk about 2 friends who's rolling a die. A die is a singular form of dice, ladies and gentlemen. Dice means more than one. Out of 8 rolls, made a 4 came up 7 times. A myth predicts the next roll will be likely not be a 4, since each number has an equal chance of being rolled. Maria decides the die is unfair since 7 out of 8 roll revealed 4. So when it comes to this situation, we need to think about 2 people in here. The first person that I'm going to consider is a myth. The one who would predict the outcome that will be not be 4. For this person, I like to put this highlight portion. A myth suggests that it's not going to be 4 because every number has an equal chance of being rolled. So in this case, it says the dice or a die, it seems like it's 1/6. It really didn't say 6-sided, so I'm assuming this person was saying 1/6 probability for probability 1, 2, 3, 4, 5, 6, 7. Oh, sorry, there's no 7, all the way to 6. So in that situation, a myth was using theoretical probability as the main part of the argument, and that was it. There is no subjective judgment based on that because it's based on our mathematical calculation of theoretical probability 1/6. On the other hand, if you think about Maria is thinking about it is unfair because 7 out of 8 roll. So imagine there's her table. 1, 2, 3, 4, 5, 6, 7, 8. There were 4, 4, 4, 4, 4, 4, 4, something like that. 7 out of 8 roll turned out to be 4, and then whatever the first one, question mark, something like that. Based on that experimental probability, she ran to the conclusion that the whole event is unfair, so subjective judgment was also occurred based on experiment. That is something that I can share as an answer. Alright, the next one, number 3. We're talking about baseball game with McGuire, and then I accidentally put name Alice, so think about McGuire down there. So in that situation, let's read the first statement. In the next game, suppose McGuire goes up to the bat. What is the probability that he will get a hit? So first thing first, the previous data suggests 2 hits for every 5 times. So that means statistic is 2/5, which is 4/10, which is 0.4, thus 40% of the chance. Based on the previous statistic, experimental statistic, or experimental probability, if you will, because that's the data that we have. Then in that case, suppose McGuire goes up to the next bat, what will be the probability? Well, we are best betting that it's 40% probability. What assumption did we make? Well, we assumed that this experimental probability should somehow apply as a theoretical probability. That is our biggest assumption that we made throughout this scenario. For each assumption, explain how the predicted outcome might change if the assumption changes. So in this case, we need to predict the outcome. There are 2 different types that I can think of. One of the probability is, okay, there is a hit. The next can be miss, obviously, so strike situation. Then, because of that, our sample size change. Because if, let's assume, there's a hit coming out, I know that the probability on the top shows 2 hits for every 5, and now that changed because we have 1 more hit, so that's 6, and instead of 2 hits, now we have a 3 hit because of that successful rate, and that is 1/2, 0.5, that's 50%. The experimental probability went up. On the other hand, if you miss, so if McGuire missed the next bat, then the number of hits changed from 5 to 6, but the hits still remain as 2. That's 1/3. That's 0.333 repeating, and that should be about 33%. So as you may notice, because of those change in an assumption in this case, the statistic value change quite dramatically. This is one of the reasons why I sometimes really emphasize of the sample space below, because imagine if we have a lot of total data, then we will have minimization for the prediction and how the percentage will change dramatically based on that. The next one. Kim wants to learn how to do snowboard but does not want to take lesson. He found an article that says below 68% snowboarding injuries occur during beginner lesson, and explain how Kim can use this statistic to support his opinion. So Kim doesn't really want to go for a snowboarding lesson because of this highlight 68% of snowboarding. Well, let's think about mathematically. First thing first, 68%. You guys may agree that this will be close to 70% if we round it up. 70% is a fancy way of saying it's way more than half. It's in fact 7 out of 10 situation we have a number of injuries. So there's an assumption that I did. I assumed that the sample space, or sample size in that case, sample size was simplified as 10. I could say 102, then in that case 70 out of 100, which is still big. But based on my statistic of rounding up, that's another big thing, sample size and round up. Due to those two, Kim could suggest that because it injures 7 out of 10, I do not wish to take lesson. Something like that. That can be one of the answer part, if you will. So far from the day 1 and day 2, we learned everything about how experimental probability can be dramatically different than theoretical probability, and how going through some of the example that we did as a yesterday homework, we know several factors that affect those, or some of those subjective judgment is kind of impossible to ignore. So we have a lot of homework today. At 427 page of Math Makes Sense 9, I want you to do 3 and 5. The next page, 8, 10, 12. And 14 and 17 must be the next page that I forgot to put. So can you double check a page 429 of the textbook for this one? So those are your to-do list. Tomorrow, or the next lesson, I want you to understand that I won't go over the homework question that I assigned for this one. I want you to use my one-to-one Google Meet time for that.